Hello. In the last several lectures, we did a quick overview of traditional machine learning approaches. In this first case study, we're going to have a physical problem, and we're going to look at a traditional machine learning approach, in this case, neural networks. And we're going to step-by-step add some of the underlying physics during training to enhance the predictability of the model. As before, all the slides and codes are provided in the website, composites.uw.edu/AI. So let's first talk about the example. And if you're not familiar with heat transfer problem, that's not an issue because these are meant to be diverse. The case studies are meant to be diverse physical phenomena, so you don't need to be expert in all of them. But I'm going to explain to you some of the underlying physics as we go further. So in many applications, it could be scientific engineering applications, we have to heat up different materials. The most efficient way of doing it is using convection. So there's a convection oven or convection autoclave shown here, where we are placing some metallic components inside them. So these are metallic components. So we get a metallic component, and this becomes sort of like a dish that holds what goes on top of that. So these are these components shown here. And then on top of that, we place something that we're going to heat up. So this becomes sort of like a dish or tool, and this becomes what we want to heat up. And then around that, we have a convective airflow. If you think about it, this is very similar of you cooking like a steak inside your oven. So you have a dish, you put a steak on top of that, and you put it inside your convection oven or inside your air fryer, and you're heating it up via convection. So we're going to increase the complexity of the problem by adding one more thing here. And it is this that we want to heat up is an epoxy-based material that can generate its own heat as you are heating it up. So we're going to describe that in a second. But if you think about it, you have a convection that is happening around a metallic tool that holds an epoxy part. So it's a convective heat transfer. Then the heat has to diffuse and goes through the part and tool from both sides. So you have conductive heat transfer. So that's the second physics that is here. And this part might produces its own heat. And that becomes, we call it polymerization heat generation. So it becomes the third types of heat mechanism that is happening here. So it's, what happens to this scenario is that there's a competition between three physical phenomena. There is a convective heat transfer, conductive heat transfer, and heat generation. And again, if you're not familiar with heat transfer, it's not an issue. The point here is there are competing mechanisms. And I selected this example specifically because at different corners of the domain, one or more of these mechanisms becomes dominant. And it becomes very challenging to predict what's happening beyond a dataset zone. And that becomes also challenging for machine learning model to capture the true behavior. So I'm going to explain to you what is it that we are trying to predict in this example. And again, the heat transfer is just an example given here. You can think about it as any other complex multi-physics problem you're dealing with. So when you are heating something on a metallic dish using convection, if you look at the temperature that you're setting for the air, this could be the temperature of your oven, for example. Even if you're baking something in your oven, you set it like to 350 F, for example, 180 C, let's say here, and you hold it for an hour or 2 hours. So what will happen is that initially oven is heating up, that's the blue line, and it takes like a half an hour or what, or 20 minutes or what to get to the temperature you want, and then you hold it to cook the part that you want to cook. Again, this follows the exact same logic as cooking something like a steak in your oven. If you look at the temperature at the center of what you're trying to heat up, that's the part temperature. At any given point initially, any temperature that you set, the temperature of the part is colder than the temperature of the air. So there is a lag between them. The reason that you have a lag is the exact same reason when you put a steak in your oven and you heat it up, its center is always colder than the outside because it takes time for the energy to go through the convection and then through conduction to get to the center of the part that you want. So there is a lag. If you had a normal steak in this case, the behavior here would be different. Here, when you heat up an epoxy, at some point, it starts generating heat. So it wants to transfer heat outside of itself to the environment. So you'll get an area where the temperature goes beyond the temperature of the air. So there is a difference now here. And the difference here is because this part is now producing its own heat. Here. So this is producing its own heat. So in this case, what we're trying to do is predict the maximum temperature as a function of few parameters. One is the thickness of this tool. If you have a thicker tool, it becomes more difficult to heat up something. You've also experienced that when you're baking or cooking something. So as a function of this thickness. Two, as a function of air velocity, that basically affects the heat transfer coefficients, how efficient the energy goes from the air into the part. And third thing we're gonna look at, so let's call this the heat transfer coefficient. We're gonna call them H, or heat transfer coefficient, and this H is related to the speed. And this heat transfer coefficient, if you're familiar with it, has a unit of, in this case, we're going to use the standard unit, watt per meter square Kelvin. And again, the actual numbers are not important. What is important is that these are variables. And what we're trying to predict is Tmax. So there is a Tmax, which is a function of this L and this H. Sorry, I'm going to write it here to be more clear. Yeah, there is a Tmax, which is a function of thickness of the tool, and then heat transfer, which is basically the speed, how much fast the air flows to produce convection. Higher the convection is probably better. You might think that thinner the tool, it might be better, but it might not be. So it's actually, since it's competing mechanism, it's very difficult to set initial correlations, the simple correlation. So it becomes complex as we go through this. So again, the actual example, which is heat transfer, is not important. For us, the important thing is we have a problem where two parameters are varied. But it's a physical problem now. The two parameters that are varied are the thickness of a tool and the speed of the air in a convection oven. And what we are trying to measure is maximum temperature that what we are trying to heat up, in this case an epoxy part, inside that 2 hours, 3 hours time period in the oven. Okay, so a CSV file has been provided, data CSV. There are 100 rows. Every row has 3 columns. The heat transfer coefficient value, the tool thickness value, and the maximum temperature measured for the part value. You can think about it as all the experiments that have been provided to you. And again, what you're trying to predict is Tmax outcome. 2 inputs, 1 outcome. At this point, you can switch up all your understanding of the physics. You don't care about the physics for the first approach. All you care is that I have given 100 data points. And I want to predict T maximum as a function of 2 of those 2 main inputs. Can I do that without enforcing any underlying physics? But I'm going to make this a more complex problem. We're going to make the problem like this. All this tool thicknesses and heat transfer coefficients values are given for a specific area. And that specific area is somewhere where the tool thickness varies between almost 5 centimeters and 3.5 centimeters. And the heat transfer coefficient, which is correlated to the velocity of the air, has its own range, and it ranges between 10 to 50 watts per meter square Kelvin. So that's the area that you have the data. We want to predict the behavior outside of that zone. So you want to train a machine learning model based on given data, and then extrapolate to the area where the tool thickness is less than 3.5 centimeters, or heat transfer coefficients are more than 50 watt per square meter Kelvin. So that's what we're trying to do. And we're going to do this, again, using two approaches. We're going to use it using machine learning approach, and then we're going to infuse physics. But the way we're going to do physics are step by step, and we increase the complexity. So we're going to have 4 different approaches, and for each approach, I'm providing you with a Python code that you can go through. So let me explain the 4 different approaches. So there are 4 Python codes that are provided. First is for a traditional machine learning using a simple neural network. So heat1.py. And I'm going to explain this time the details of how the coding is done. The second one is what are called physics-informed features. It's a technique for physics-informed machine learning. The third approach, we call it physics-informed loss. We're going to modify the loss functions based on the underlying physics. The fourth option is a much more powerful approach compared to the other two. I'll call it physics-informed domain transformation. And you can kind of see that this gets very close to capture the true behavior way outside of the training zone. And the last one, I'm just going to explain it because the implementation is quite complex. I'm not providing the Python codes. I have published a paper on the last approach, and I provide you the details. If you're interested to learn more, you can take a look at that paper. Okay, so let's go step by step into these 4 approaches. So in this lecture, I'm going to finish the traditional neural network, and in the last lecture, we're going to go over the other methods. Okay, so Python implementation to train a neural network. So we are going to use a Python library called TensorFlow from Scikit. TensorFlow and Scikit library. So we're going to import the TensorFlow as TF. We're going to import some baseline libraries like data frames, pandas, and numpys data frames. And then we're going to use specific types of models, which we're going to describe. We're going to use a specific optimizer, AdaMax, it's an optimization algorithm to train the neural network. We are going to use some components, some libraries under scikit-learn to do some of the calculations of training, and that's like splitting the data or scaling the data. And then we're going to plot the data at the end. So if you look at the whole thing, there's a couple of lines I've added at the beginning to basically hide any warnings that you might get. And then you will get into the nitty-gritty, import TensorFlow, and build the neural network model, set the optimizer, modify the data, and then train and then plot the data. So let's go step by step. If you look at the code that is provided, first you're importing the CSV file. The data file is imported, and you're then creating Pandas framework. If you're not familiar with Pandas framework, it's a labeled structured data. So basically what you will get is labeled data where you have L and H and T max, and then you get row 0 to row 99. and I can use this for training a neural network. It's very simple to get Pandas framework and then use that for training of the machine learning. The next is you want to prepare your data. So what we are doing here, L and H and T max, they have their own units and their ranges are quite different. It helps a lot if you scale your data. So that's what we have done here. We are using a standard scaler. So you can scale your data between -1 to 0 or scale it based on mean and standard deviation. And that's what we have done here. And that makes the training much easier. Then the training is a split. So you will split the data with 25% for validation and 75% for training. So you train the data with 75% of data, 75 data points, and then you check the accuracy of that on the 25% data point. And then I have four, if you think about it, I have 4 matrices at the end: training X, outcome X, outcome of the training, which is Y train, X test, which is that 25%, and then Y tests. And then you can do the training of the neural network afterward. We're going to train a specific neural network, 2 inputs, L and H, and then 1 output, T max. There are 3 layers and 16 nodes per layer. We are using a specific optimizer called Aeronautics. You can modify these things, of course, but that's not the point. The point here is to see the efficiency of an approach like this to predict what's happening outside of its training zone. But in order to select this, I have done some hyperparameter optimization. So these are not randomly selected. There's some analysis done before this to select this. And then we're going to look at the mean squared error as the loss. So this is how we are, this section of the code, which is a function, shows you how we are building and how we are training and how we are evaluating the model. So first there's basically a loop that has these layers, these hidden layers. Then we train the model. The model fit, and then eventually we evaluate the model. And we evaluate the model by prediction outcome, which is like R2 test. In addition to mean squared error, we are also looking at percentage-wise accuracy of the model. So this is the outcome of the model. After you do the training, again, you can do this with the Python code yourself. We will get a 98.6% accuracy. Test accuracy. So if you look at this data points that are shown here, these are the 100 data points. These are divided into 25 random data points test, 75 random data points training. The training is done on that 75, and then we test if it's accurate on that 25 data points. And we get an accuracy of almost 100%. Then what we have done here, these surfaces that you see, the same trained neural network is extrapolated beyond the training zone to the area that we are interested. And if you look closely, it seems like the neural network takes the slopes and then extrapolate beyond its zone, but it's not always the same. So if you repeat this training over and over, you might get different results. But the bottom line is it thinks what's happening beyond its zone is more or less constant. Not much ups and downs are happening. Okay? So there is a separate CSV file provided, which has close to 1,000 data points, and that's well beyond the training zone. And we're keeping it hidden, so the training algorithm doesn't see this. But we just check it now if the extrapolation is actually correct beyond the training zone. So the blue dots are those experiments that were done outside of our training zone. Those are the extrapolation data. And you can see how wrong the predictions are based on this simple neural network. In both directions, we are making a mistake. If you look at this, this corner, the prediction of the neural network is that the T max value goes slowly up, while the extrapolation shows is almost no change beyond a certain point. But the other side is more serious. It actually predicts something which is much, much higher than the baseline that the neural network predicts. And that shows that it's actually absolutely incorrect if you take that trained neural network and try to predict what's happening in this zone. And again, no fault of the neural network at this point. There is no reason that it should predict what's happened. The whole idea that if you have data, the neural network can capture the underlying physics is only true for that corner of the domain that it has seen data. It has no clue what's happening outside of it. Even though the physics is consistent, the reason it cannot capture what's happening here is because the dominant physics mechanism is changing. There are 3 competing mechanisms here. And then each of them, or 2 of them, might become dominant in a corner, and the neural network has no clue that that's happening. So in the next section, I'm going to show you through different approaches how we can change this, how we can mitigate this issue.